join doang Pak, bikin join terus di erection di atas, dipasang. Jadi urusan kita cuma bikin join sama erection join Pak. Jadi yang bikin join ini nomor satu, dan join ini jadi kita harus develop nomor satu adalah actual join mockup. Itu yang kita lakukan. Begitu itu jadi baru gedung, baru kita bisa kerja selanjutnya. Dan ini yang salah satu tahapan yang terpenting adalah actual join mockupnya itu masukan dari seluruh pihak yang terkait Pak. Nah ini engineering proses kita pakai BIM, besok kami jelaskan secara lebih komprehensif. Sekarang cuma sekedar ininya aja, slide pengantarnya, silakan lanjut. Ini BIM proses kita, engineering shop drawing proses kita pakai ini dari 3D, dari data dari 3D menjadi 2D. Ini lanjut. Ini Pak, dari gambar mockupnya sampai jadi mockupnya. Belum ditutup mockupnya, masih terbuka supaya bisa dilihat, diinspeksi oleh seluruh konsultan dan konsultan perencana dan oleh owner team. Lanjut. Sekian Pak, yang untuk hari ini sebagai pengenalan saja. Besok kami lanjutkan yang detailnya Pak. Terima kasih.
Saya mau tanya pertama buat perencananya dulu. Jadi selain aspek kekuatan kan kita perhatikan serviceability. Nah saya penasaran untuk bagian seperti sayap-sayapnya dan sebagainya. Ya. Berapa nilai deformasi yang bisa ditoleransi? Kemudian juga terhadap vibration. Kriteria apa yang digunakan? Dan setelah gedungnya jadi, apakah juga pernah ditinjau untuk memonitor bagaimana deformasi dan vibrasi yang terjadi pada patung tersebut. Kemudian untuk fabrikator, saya mau tanya sebenarnya pada waktu metode erection apakah pada setiap step dilakukan analisis stability-nya? Dan saya percaya kalau mau ngelas Bapak pasti bikin dulu WPS dan PQR-nya ya. Mudah-mudahan besok bisa di-share terhadap yang lain supaya rekan-rekan itu semua mengerti kalau kita mau ngelas ada prosedur yang harus dilalui pertama, yaitu membuat WPS dan PQR-nya. Terima kasih.
Baik, saya coba jelaskan sedikit ya. Memang untuk tadi serviceability, deformasi ya kita ada toleransi ya, kita mengikuti spek ya Pak ya. Itu kalau kita lihat di spek itu kurang lebih L per berapa ya? L per 300 gitu sesuai yang di spek Pak. Saya waktu itu lupa ngelihatnya. Dan juga untuk deformasi atau refleksi ini ada bantuan juga dari tim yang di lapangan itu selalu mengecek ya. Jadi berapa deformasi pada saat erection yang sudah terpasang itu dicek. Dia turun atau bergeser berapa dan kita lihat gitu. Memang ada beberapa mungkin di toleransi di kemiringan ya. Jadi ada yang kemiringan harusnya di titik ini ada bergeser kurang lebih sekitar 10 sampai 15 mili ya, tapi kita perbaiki di atasnya biar kembali ke verticality ini. Jadi tentu itu hasil studi dari RWDI-nya Pak kalau yang di wind tunnel test itu. Jadi hasil dari mereka kita pakai rekomendasinya aja. Jadi rekomendasi mereka berapa kecepatan angin yang berpengaruh di sini. Nah itu kita hitung dan menjadi beban tadi ya, cladding dan juga per lantai bangunan. Jadi kita bisa aplikasi. Tentu mereka sudah melihat ya, jadi dari model tadi itu ada perputarannya ya, per berapa derajat itu dites dan mereka bisa tabelkan hasilnya mana yang paling maksimum kurang lebih mungkin begitu. Kemudian ya mereka sudah studi semua tentunya ya.
Selamat pagi, kenalkan nama saya Ito from Tokyo. I would like to start our presentation. The title is, first aspect, disaster and seismic retrofit of building in Japan. So I'll start my presentation. So first is past earthquake disaster and the transition in seismic design code in Japan. Japan is a prominent earthquake-prone country. This figure indicates the relationship between the Japan island and the tectonic plates on the surface of the Earth. It shows that Japan island is situated at a complex junction where the Pacific plate meets with the Philippine Sea plate and the Eurasian plate meets with the North American plate. So this slide indicates the major earthquakes that have occurred in Japan in the past and the corresponding change in seismic design code. Japan's seismic design code are stipulated in detail in the building standard and include design methods and the specifications that are different from those found in other countries. This slide shows a typical damage that caused by the earthquake. RC buildings were damaged in many places. One specific characteristic of the earthquake damage was the so-called shear failure, occurred to many of the thick but short columns that were a common construction feature of school building in Japan. Following the damage caused by the Tokachi earthquake to RC column triggered by the damage in the earthquake, the building standard of Japan was revised in 1971. In order to prevent a column from suffering the type of shear failure that was observed as a result of Tokachi earthquake, the law was revised so that the distance between hoop reinforcement in the column should be narrower, as shown in the figure on the left. Due to the damage caused by the Tokachi earthquake and the development of response analytical technology, it became necessary to drastically revise seismic design method by incorporating dynamic properties and condition. As a result, Ministry of Construction Japan implemented a comprehensive technology development project called Development of a New Seismic Design Method for 5 years from 1972. The damage caused by the Miyagi earthquake of 1978 proves the validity of the new design method. And in 1981, the building standard law underwent drastic revision, establishing the so-called the new seismic design code. The seismic design code established technical standard based on the goal listed below. 1. Building must be damaged by medium-scale earthquakes or similar earthquakes that they are likely to experience at least one or more times during their service lifetime. 2. Building must be destroyed, collapsed, or otherwise be damaged by rare large-scale earthquake, whose occurrence is so quite rare that they are likely to experience them only one or not during their service time. The seismic design method is generally used in Japan even today. The new seismic design code stipulated that it's a rare scale earthquake occur. Building must have the required lateral capacity that is set for the ability of each framework to deform, ductility. In this figure, the vertical axis indicates the load-bearing capacity of a building, while the horizontal axis indicates the building ability to deform. A seismic structure refers to a structure that can withstand assumed seismic force in terms of strength and ductility. Strength refers to a load-bearing capacity high enough to withstand seismic force, and the ductility related to the deformation ability high enough to withstand seismic force. The lateral refers to the maximum load-bearing capacity in the plastic deformation area in this figure. These are proposed design method for tsunami refugee building. The formula to calculate tsunami water wave pressure is proposed. These are examples of proposed tsunami refugee buildings. Proposed in the upper left illustrate is an urban district entirely elevated for tsunami. The upper right picture shows a proposed tsunami refugee building. Lower pilot column used concrete filter tube, a CFT structure, to protect steel from driftage. Another major lesson learned from the damage caused by the Great East Japan earthquake is the so-called long period seismic motion. The long period seismic motion refers to large vibrations that occur over a long period of time to highlight base isolation, and the other building whose natural period is long because of long period seismic motion caused by a huge subduction zone type earthquake. It will be necessary in future to promote further explanation of these long period seismic motion. The following 2011 Great East Japan earthquake, which exceed all of our prediction, review of the huge earthquake expectations that are likely to occur in and around the Japan islands are underway. This map indicates the assumed source area along the Nankai Trough, where a huge earthquake is highly likely to occur in near future. The expected magnitude is 9.0, the same as for the 2011 Great East Japan earthquake and the 2004 earthquake of Sumatra in Indonesia. I'll complete the presentation of chapter 2. The next slide presents example of damage to component other than the main structure member. This is one of the characteristics of earthquake damage. The collapse of a connection passenger bridge was observed. In the photo on the left, a corresponding corridor bridge was installed on each story of two adjacent condominiums. But since the first floor of the left condominium was destroyed, then all of the connecting corridor bridge fell accordingly. On the other hand, the photo on the right shows an example of damage to the connecting corridor bridge between two office buildings. The upper connecting corridor fell, but was supported by the one below it. The below corridor support the upper bridge. Next, please. The next slide indicates an example of damage to steel frame building. The first example is of damage to the main steel column on the mega frame of high-rise condominium. As shown in the photo on the left, part of the main column, which is surrounded by broken red line, broke. On the right-hand slide is an enlarged picture of the broken part. The main steel column broken first, and then breakage propagated to the diagonal bracing. The next slide indicates an example of damage to column to beam connection in the structural framework combining steel tube column and the H-shaped steel beam, which is often seen in medium to low-rise steel frame building in Japan. As shown in the photo on the right, the steel base material of flange from the bottom flange of the H-shaped steel beam to the web plate block. Figure 2 shown a typical example of breakage seen in the column to beam connection. 4 locations from 1 to 4 are cited as example of breakage point, but the most frequently observed damage was the rupture of the steel beam flange base material, which started from the web scallop welding hole, number 1 location. One of the characteristics of other type of damage caused to steel frame building was damage caused to vertical brace. The photo on the left shows an example of damage to a 7-story steel moment frame building with vertical bracing, and the buckling of a K-shaped brace that used H-shaped steel was observed. Meanwhile, the photo of the right indicates an example of damage to another building of structure with bracing, which was 8-story, and the buckling of bracing with T-shaped cut steel materials used face back to back. Next, one of the examples of damage to steel frame building that were most often observed was damaged column base. The photo on the left indicates a 6-story building with a rigid frame structure, which experienced the tensile rupture of an anchor bolt in the column that used a square steel tube. The photo on the right, on the other hand, shows a 3-story building with a rigid frame structure, which experienced out of frame bending of the base plate of the column that used H-shaped steel and the crack in the welding part of the flange of the H-shaped steel column edge of its base plate. Finish. This is photo of a response control brace installed along the corridor between the 2 buildings. 1 unit of brace, 2-story height. So, second is parallel